Hello and welcome back. In this video we'll be looking at average rates of change. And this should be a fairly straightforward lesson, but I do want to go into some detail here. So an average rate of change is going to be the total change in value divided by the time taken to change. So this is, again, this is going to be fairly straightforward. So for instance, in 1960, Havre's population was 10,740, and in 2010, it was 9,301. So the question is, what was the average rate of change in Havre's population? So first things first, we should find out what was the actual change. Well, if we take 10,740 and we subtract 9,310, we'll get 1,430. Now, the thing is that our population decreased. So the total change in population is actually going to be negative. So we want negative 1,430. So this is important. If a value decreases, we need this to be negative. If the value increases, we want it to be positive. The time, if I take 2010 and I subtract 1960, that'll be a span of 50 years. So the total change is going to be that many people. And the total time is going to be 50 years. So on average, so our average rate of change, which we'll just call R, is going to be negative 1 divided by 5. And I will try to simplify this as much as I can. So let's cancel off a factor of 10. 14 divided by 2, 43 divided by 2. So on average, Havre has lost 28.6 people, and the units here are important. The negative 1,430. This was the number of people, and this on the bottom is going to be years. So it's going to be negative 28.6 people per year. And when we're looking at average rates of change, typically the units on the bottom are going to be some unit of time, and the unit on top will be whatever we're looking at that is changing. So here our population is just measured in people. So Havre's going to be losing, again losing because we have a negative sign here, losing 28.6 people a year on average. Now, does this mean that Havre loses exactly 28.6 people every year? Well, no, because you can't lose 0.6 of a person. So again, this is only average. So some years it'll be more, some years it'll be less. This is never going to be exactly right, or I should say hardly ever. So if we want the rate of change in something, so here's a more exact formula, but this should make intuitive sense. Again, you look at the change in the y value, as in if we're looking at y, we want to see how did y change versus how long did it take to change. So the change in the y value, we would normally take the last value minus the first one. So if it went up, we'll take the bigger number minus the smaller number, so we should get a positive number. But if it went down, taking the later number minus the earlier number, we'll get a negative number, and we'll see that the population, and we'll see that the value decreased. So let's go through an example that doesn't necessarily have units associated with it. So let's find the average rate of change for this function, f of x is equal to x squared minus x, from x0, which is 0, to x1, which is 1, and then from x1 to, which is 1, to x2. So what we want to do is find the average rate of change. So from x1 to x2. So let's do this one first. So from x1 is equal to 0 to x1 is equal to 1. So we should figure out what our function is equal to at 0 and at 1. So f of 0 is going to be 0 squared minus 0, which is 0. And f of 1 is going to be 1 squared minus 1, which is also 0. So how much did this change? So the change in our function value divided by the change in x. Again, x might represent time here or something like this. The change in f would be f1 minus f0. And then the change in x would be 1 minus 0. f1 minus f of 0, well, that's just 0 minus 0. 1 minus 0 on the bottom. So we get 0 divided by 1, which is 0. So on average, this function doesn't change from when x is equal to 0 to x is equal to 1. And we can see that right away. We didn't even have to do the calculation. It started at 0 and it ended at 0 at 1. So whatever the function height does in between, maybe it shoots up, maybe it shoots down, maybe it squiggles all over the place, it starts at 0 and ends at 0. So on average, nothing changed. So on average, our average rate of change is going to be 0. If we look a little bit further and we look at x2, which is 2, f of 2 is going to be 2 squared minus 2. 2 squared is 4, minus 2 is actually going to be 2. So if we want to look at the average rate of change a little bit later, this will be f of 2 minus f of 1 over x2, which is 2 minus 1. And what we see is that we'll have 2 minus 0 over 2 minus 1. It's going to be 2 over 1. So our average rate of change is now 2. So the average rate of change in our function changed from 0 to 1. It's as if it didn't move. On average, it didn't move, but it could have wiggled a lot in between. From 1 to 2, though, it did increase by 2. So what I want to do is draw a picture, and I'll point something out here. So here is our picture of f of x is equal to x squared minus x. So we have our x-axis and our y-axis, which is going to be going to denote the height of our function. And from x is equal to 0 to x is equal to 1, we'll see that, yeah, this height doesn't change. So on average, from 0 to 1, our function does not change. Now, this is only on average. This is not sort of in total. You'll see that this is a parabola, and we're still going down as we come away from 0, and then we go up a little bit later. But because we go down and then up, those cancel out, and on average, this function is not changing at all. Whereas from x is equal to 1 to x is equal to 2, you can see that the difference between these guys is going to be a little bit more significant. We've increased from x is equal to 1 to x is equal to 2. And then that increase is given by, say, this positive number 2. But when we look at what 2 represents in here, if we want the change in y versus the change in t, or in this case, in fact, we could even go, since our time or whatever it is that we're measuring is on the x-axis, I could just call this x. This is the formula for slope. So the question is, what slope is it? Well, it's if you drew a straight line between our 2 points here, it's going to be the slope of this line. Now, the actual slope of the function x squared minus x changes a lot. For instance, over here, we're coming down, so we have a negative slope. Over here, we're going to be coming up and we're going to have a positive slope. So the slope of this function changes in x, but on average, from the point x equal to 1 to x equal to 2, the average slope, or the average rate of change, is exactly 2. So rates are going to be slopes, or I should say rates of change are going to be slopes. And in the next lesson, and in fact for the next couple lessons, we'll be calculating slopes exactly of functions that aren't even straight lines, and this will be called the derivative. But we will get there in the next couple of lessons. So let's do another one. So the following graph shows the height of a ball thrown upward from the roof of a building. Find the average rate of change in height from 0 to 2, from 2 to 6, and then from 0 to 6. So again, we can draw this. So for instance, so from t is equal to 0 to t1 is equal to 2. Here is the height at time is equal to 0. Here's the height at time is equal to 2. And if we draw a straight line between them, we can see that, yes, our straight line is going up. So the average change in height should be positive, and it's just going to be the slope of this line. So again, so for number 1, we're ending at 60. We began at 50. And the difference in time is going to be 2 seconds. It's going to be 10 divided by 2. So the average slope of this line is going to be 5. Now, we are given some units here. This is going to be in feet and in seconds. So this is going to be 5 feet per second. The units are important, especially in problems in, say, physics and chemistry and biology and so on. So let's look at the change, the average rate of change from 2 to 6. So here's time equal to 2, here's time equal to 6, and what happens here is we're coming down quite fast. The ball has reached the apex, the highest point, and then starts to fall. So again, this highest point up here is going to be 60. The lowest point when it hits the ground is going to be 0. So we take the second point, which is 0, minus 60, divided by the change in time. So we're ending at 6 seconds, and we began at 2 seconds. So it's going to be negative 60 divided by 4, so it's going to be negative 15. And again, we get the same units. A rate of change is going to be how far did it fall in feet versus how long did it take to fall in seconds. So again, we get a negative number here because the ball that's being thrown is falling. The height change is going to be negative. And then the last one is going to be, okay, so it rose at 5 feet per second for the first, on average, it rose 5 feet per second in the first 2 seconds. And then, on average, it fell 15 feet per second in the last 4 seconds. But what did it do overall? From time is equal to 0 to 6 seconds. So again, what we can do is we can take the final height minus the initial height divided by the total time. So it would be 6 seconds at the end versus 0 seconds at the beginning. It would be negative 50 divided by 6. And for this one, I'll just leave this as a fraction. So this is going to be negative 25 thirds. So that's about 8, negative 8. And again, this is in feet per second. So what you'll notice is that negative 8 isn't the average of 5 and negative 15. It'll be the weighted average because it spent a lot longer falling than it did going up. And this is just a brief summary of average rates of change.